So welcome back. Let's go ahead with the last section of this chapter, volumetric changes. So here we are going to see volumetric changes due to loads and also temperature change. First of all, we are going with volumetric changes due to loads. So before going into that, we should understand the relationship between normal stresses and normal strains. That means if you know normal stresses, how to get normal strains, or if you know normal strains, how to get normal stresses. The formula here. Okay. If you have a scenario where the member is like this, there is stress in x direction, this will be giving rise to strain x direction as sigma x by E. Okay, and according to Points ratio, minus epsilon y by epsilon x gives us epsilon y is equal to minus mu epsilon x minus mu into sigma x by E. Okay, epsilon x is sigma x by E and epsilon y is also equal to, epsilon y comes out to minus mu into sigma x by E here. I am going with the same member, but other way of application of load. There is normal stress in y direction. So in this case, you can say that epsilon y is equal to sigma y by E, and Points ratio is minus epsilon x by epsilon y because load is applied in y direction. This gives us epsilon x value as minus mu into sigma y by E here. Now I am going with the case which is combination of the previous two. So this is nothing but superimposition of these two cases. So simply we can add it up. So epsilon x is nothing but epsilon x produced due to sigma x, that is given by sigma x by E. Epsilon x produced due to sigma y, that is given by minus mu into sigma y by E. Same way, epsilon y comes out to be sigma y by E minus mu sigma x by E. Okay. So this is a case where there is only sigma x and there is only sigma y. If you have a scenario where sigma z is also there, you'll be getting equations like this: sigma x by E minus mu sigma y by E minus mu sigma z by E. Epsilon y, sigma y by E minus mu sigma x by E minus mu sigma z by E. Here sigma z by E minus mu sigma x by E minus mu sigma y by E. Understood? So these equations are given the name as generalized Hooke's law. These are given the name as generalized Hooke's law. Okay, so and again, as we are giving the name as Hooke's law, kindly remember that these are valid for only mechanical cases of stress and strain. Valid for only mechanical cases of stress and strain. Mechanical cases of stress and strain. Okay. So based upon this formula, you can solve this question. After this, we'll go with the first part of this section, that is volumetric changes due to loads. If you see the question, there is pressure acting in x direction in a compressive way and y direction also in compressive way. Okay, so pressure, whenever it causes a stress, it will be giving rise to compressive stress. So sigma x is 250 megapascal, sigma y is also 250 megapascal in a compressive way. Sigma x is equal to minus 250 megapascal, sigma y is also minus 250 megapascal. Now to get Points ratio, we need epsilon x, epsilon y also. In this one, if you see epsilon x, it is final length minus original length by original length in x direction. Final length in x direction is nothing but L minus 2 delta and original length is equal to L. So this gives us the value as minus 2 delta by L. So epsilon x comes out to be minus 2 into delta, that is given as 0.001. Original length is equal to given as 2 meter. So epsilon x value comes out to be minus 0.001. In the same, if you do calculation, epsilon y also comes out to be 0.001. So you should remember that epsilon x is, strains are coming out to be in negative and stresses are also in compressive way. So let's apply this condition. Epsilon x is sigma x by E minus mu sigma y by E. I am not putting z because there is no stress in z direction. Okay, So if I substitute in this one, I can get the value of mu because I know everything. In this question, they are given Young's modulus as gigapascal, 200 gigapascal. So epsilon x is equal to minus 10 power of minus 3 is equal to sigma x minus 250 into 10 power of 6 by 200 into 10 power of 9 minus mu into minus 250 into 10 power of 6 whole by 200 into 10 power of 9. If you simplify this comes out to be minus 10 power of minus 3 into 200 into 10 power of 9 is equal to minus 250 into 10 power of 6 whole into 1 plus mu. This gives us, if you simplify, minus 200 into 10 power of 6 minus 250 into 10 power of 6 into 1 plus mu. 1 plus mu is equal to 20 by 25, 4 by 5. So mu is equal to 1 minus, 1 plus mu is equal to 20 by 25, 5 4s, 5 5 is 20. So mu 4 by 5 minus 1, no, there is some mistake here because we are getting negative value of negative value here. So epsilon x is this one here, minus, oh, here you will be having minus sign only because we are taking out minus 250 megapascal outside. So minus only here, minus. So 1 minus mu is this value. Mu comes out to 1 minus 4 by 5 is equal to 1 by 5 is equal to 0.2. This is how you have to solve this question. Okay? Let's go with the volumetric changes due to loads, first part of this section. We're going to use this generalized Hooke's law result. Okay? Kindly put the title. I'm rubbing the board. I hope everybody have got the answer. So here we're going to apply these Hooke's law equations here. Volumetric changes due to loads. First of all, we'll look into volumetric changes due to loads or stresses due to a rectangular bar or for a rectangular bar. So you're taking a rectangular bar like this. It's having one of the dimension along x-axis, another dimension along y-axis, and so on like that. So this is x, so this is y, and this is z. If you take volume of this rectangular bar, it is nothing but length into breadth into height. So if you do partial differentiation, it becomes LB into DH. So B into H into DL plus L into H into dV. You divide by volume on both sides. LBH, LBH, LBH. dV by V is dH by H plus dL by L plus dB by B. If you see here, these are nothing but strains in three perpendicular directions because one of the dimensions is along X, another dimension is along Y, another one is along Z. So it can be written as, so this is a very standard formula. In fact, we are going to get the same answer for other shapes as well. So that's why we are going to take cylinder as well after this one. Okay. In this one, if you substitute these equations, generalized Hooke's law equations, epsilon x is like this, epsilon y is like this, and epsilon z is like this. Substituting in this equation, you will get epsilon v as 1 minus 2 mu by E whole into sigma x plus sigma y plus sigma z. Epsilon v is 1 minus 2 mu by E, sigma x plus sigma y plus sigma z. So here, to derive this equation, we haven't used generalized Hooke's law. But to derive this equation, we used these equations, right? Understand? So, this equation, the first equation will be valid for all cases. But this equation is valid for only mechanical cases of stress and strain. It's valid for only mechanical cases of stress and strain. Okay? Clear? So kindly copy this. You can get the answer for this question. Yeah, very good, Vikram. So the answer is B here. It's given that a 200 into 100 into 50 millimeter steel block is subjected to a hydrostatic pressure of 15 megapascal. So whenever pressure is acting, that will be giving rise to compressive stress. So it is experiencing change of volume. So stress is acting in every direction. So sigma x is equal to sigma y is equal to sigma z. All are equal to minus 15 megapascal. Dimension volume of the block is also given. Young's modulus and Poisson ratio are given like this. Young's modulus is 200 gigapascal. Poisson ratio is equal to 0.3. The change in volume of the block in millimeter cube. So you have to get the value of change in volume of the block. So we have the answer for volumetric strain, formula for volumetric strain as 1 minus 2 mu by E whole into sigma x plus sigma y plus sigma z. So this gives you actually change in volume by original volume. So it's a dimensionless quantity. So this is a dimensionless quantity here. So let's get this value. 1 minus 2 into 0.3 whole by Young's modulus 200 into 10 power of 9 whole into sigma x plus sigma y plus sigma z will become minus 15 into 10 power of 6. Okay. So this gives you change of volume. So if you want to get change of volume in millimeter cube as it is asked in the question, you should substitute volume also in millimeter cube. So I'm substituting as 200 into 100 into 50 millimeter cube. If you simplify this, so you'll get this value as 0.6, 1 minus 0.6, this becomes 0.4. So here we have minus 45, here 10 power of 6 is there, here we'll be getting 10 power of 3. Okay, so 10 power of 3 is there and two values 10 power of 5. So you'll get it as minus 0.2 into 45 into 10 power of minus 345 minus 5. So it is nothing but 45 2s is 90. So it becomes minus 9 into 10 power of minus 5. So if you take this thing that side, delta V will become minus 9 into 10 power of minus 5 into 5 into 2, 10. 10, 1, 2, 3, 4, 5. So another, so already 10 is there. So this gives you minus 90 millimeter cube. This means the member is experiencing decrease of volume. So volume is decreasing here. That's the answer for this question. Now you guys can go with the next question. So very good. For this question, the answer is C. It's given that an elastic isotropic body is in a hydrostatic state of stress as shown in the figure. For no change of volume to occur, what should be its Poisson's ratio? So we have a formula for volumetric strain or change of volume by original volume as 1 minus 2 mu by E into sigma x plus sigma y plus sigma z. I'm taking this equation because we are going with hydrostatic state of stress. That means due to pressure, sigma x, sigma y, sigma z are produced. So here, some stress is there because pressure is being applied. So this value is non-zero. Okay? They are saying change of volume by original volume is coming out to be 0. So here you see 0 is equal to 1 minus 2 mu by E whole into sigma x plus sigma y plus sigma z, which is non-zero. So the product should become 0 means one of the values should become 0 here. So the only other choice is 1 minus 2 mu by E is equal to 0 implies Poisson's ratio is equal to 0.5. So we got the same answer using other method, taking k is equal to or bulk modulus k is equal to infinity. Okay, so we are getting volumetric change is equal to 0. So this happens only for incompressed materials. In this way also we can derive and say that for an incompressed material, Poisson's ratio is 0.5. Clear? Understood? Let's go with the next shape, that is cylinder. Those people who are a little bit new. So I hope people are following. There is no confusion, I hope. Let's go with the next shape, that is cylinder. And then we'll go and see a couple of numericals regarding that, and then we'll go into volumetric changes due to temperature change. Last part of this chapter. So cylinder, if you take it, I'm taking the cylinder like this. Length is along x-axis. So it's one of the diameters along y-axis, another diameter is along z-axis. If you take volume, it is nothing but pi d square by 4 into length. Let's do the same process. So it becomes pi d square by 4 into dl plus pi into 2d by 2d into dd into L. So pi by 4 into L and 2d into dd. So dividing by original volume on both sides, pi d square by 4 into L whole by pi d square by 4 into L. If you divide, you will get it as dv by v as nothing but dl by L plus dd by d. Here, if you do the partial differentiation for diameter, it is twice of radius. So dd is nothing but twice of dr. If you divide by diameter on both sides, it becomes dd by d is equal to dr by r. So you can write down this thing as dl by L plus dr by r. Sorry, you're having 2 here. I'm forgetting about 2 here. So it is nothing but dl by L plus dr by R plus dr by R, which is nothing but epsilon V is equal to epsilon x plus epsilon y plus epsilon z, because we are having one of the radius along y direction, another radius along z direction. Understood? So we'll be having like this, epsilon V is equal to epsilon x plus epsilon y plus epsilon z here. Understood? So but generally it is written as epsilon V is equal to epsilon L plus 2 into epsilon R. Instead of writing in terms of x, y, z, it's written in terms of notations of length and radius. Okay? So y and z are strains along radial direction. So this equation, as we don't use any Hooke's law condition, this is valid for all cases. Okay, but if you take this one, after substituting generalized Hooke's law equations, we'll get the volumetric strain to be 1 minus 2 mu by E into sigma L plus 2 into sigma R. And this equation is valid for only mechanical cases of stress and strain. Once you're done with this, you can copy the next question, get the answer. Name of sigma R. Sigma R means stress along radial direction. Okay, and sigma L means stress along length direction. That's it. Okay, so for this question, if you see, it's given that a round bar of length L, young's modulus E, Poisson ratio mu, is subjected to an axial pull P. What would be the change in volume of the bar for this? Instead of solving completely, you can get the answer by using shortcut also, or thinking in a little bit different way also. We just now understood that if Poisson ratio is 0.5 means volumetric strain will become 0. Actually, we got the answer in this way. When volumetric strain is 0 or change in volume is equal to 0, the value of Poisson ratio should be 0.5. So here they are asking for change in volume. Let's substitute Poisson ratio as 0.5. You should get the value to be equal to 0, right? So if you substitute Poisson ratio as 0.5 in option number A, C and D, you will not get the answer as 0, except in the answer or option number B. So the correct answer for this question is B. Like this you can get the answer very fast. Okay, otherwise you can simply substitute as well. At the end we have to use this equation. So sigma R is anyways not there. So force is acting in, if you take this diagram, it is like this. So force is acting in x direction. So this is the value of area A. Sigma L is nothing but P by A. So volumetric strain is nothing but change in volume by original volume, that is area into length. So this area will get cancelled. So delta V comes out to be 1 minus 2 mu by E into P into L. So if you see, the correct answer is B. Clear? I hope there is no doubt. So we're done with this volumetric changes due to loads. Let's go ahead with volumetric changes due to temperature change. Okay? I'm rubbing the board. Chala Sanjay, the concept is same. If you take sphere, the only difference you'll be getting is sigma x, sigma y, sigma z all are equal to sigma r. Epsilon x, epsilon y, epsilon z all are equal to epsilon r. That's it. Same, you'll get it. Understand? If you do the derivation, also you'll be getting it. So there is nothing extra to learn there, and there is any gate question as well. There is no gate question as well. Clear? Let's go ahead with this volumetric changes due to temperature change. So here, before going ahead, we should understand one very important concept. Okay, we have one basic idea already from the linear changes that if the body is free to expand, it will be having stress 0. If it is restricted to expand, stress will be non-zero. That's very, very clear. Now, let's take the case where the member is restricted in multiple directions. So, in x direction, it is restricted to expand. In y direction also, it is restricted to expand. In x direction it is restricted to expand. In y direction also it is restricted to expand. So this is x direction, this is y direction, and this is z direction. So it's very clear already that sigma x is non-zero, sigma y is non-zero, sigma z is equal to 0. Because we already have the basic idea that if it is restricted in any particular direction, stress will be non-zero. If it is free to expand, means stress will be equal to 0. Now if you compare sigma x and sigma y, sigma x, from linear changes we understood that sigma is produced by alpha, sigma is produced by E, sigma is produced by delta T. Basically it's produced due to temperature change and depends upon the values of alpha and Young's modulus. So in x direction, y direction, alpha and E are same and we do uniform heating. So at every point, if the body is heated by or increase its temperature by 10 degrees, every point will increase its temperature by 10 degrees only. Okay, uniform heating is there. So if you see here, alpha, E and delta T are same in x direction also y direction. So we can say as alpha, E, delta T are same in x as well as y direction, we can say that sigma x value will be equal to sigma y. Okay, so you can write down like this: as for an isotropic material, because if it is not an isotropic material, x direction alpha x, x direction alpha, y direction alpha may not be same. Young's modulus in x direction, Young's modulus in y direction will not be same. So you will not be having this condition to be satisfied. So as far as you are going with isotropic materials, alpha E T will be same, delta T will be same. So you will be getting sigma x equal to sigma y. So after copying this, put this statement. So in an isotropic body, whenever it is restricted along multiple directions, when there is uniform heating, you will have same stress in those all multiple directions. Clear? So kindly copy that. So I hope it is clear to everyone. I hope there is no doubt. So whenever you have restricted directions, restricted multiple directions, you should be remembering that the value of stress is same in those multiple directions. Okay, so we'll take different cases. First of all, we are going with the case when the body is free to expand in all the three directions. Kindly put the heading. So for our understanding purpose, always I'll use the word as cube. Okay. So we are giving rise to stresses or temperature changes etc. on the cube here. So all sides are free means it will expand freely in all the three directions. So we can say sigma x as 0, sigma y 0, sigma z 0, and epsilon x, epsilon y values, epsilon z values also known to us. So they will come out to be alpha delta t. Okay, these are non-zero, these are zero, these are non-zero. If you want to get volumetric strain, it is equal to epsilon x plus epsilon y plus epsilon z. So addition comes out to be 3 alpha into delta t. So based upon this one, you can get the value of change in volume as well. Clear? So this first one is very easy because it is simply completely a thermal case. After this, we'll start with combination of both thermal plus mechanical cases. Okay, let's go with the next one. All directions are constrained. I want you people to see the derivation of this example, okay? Because we cannot mug up the formula for every case. We should understand how the derivation is done. Easy derivation only, simple condition only, so that any question, if it is coming, you'll be able to tackle that. So the cube is restricted to expand in all the three directions. In x direction, y direction, and also in z direction. All the three directions is restricted to expand. So sigma x non-zero, sigma y non-zero, sigma z non-zero. So we are taking out to be sigma because from our initial discussion we understood that when it is restricted along multiple directions, on all the directions stress will be same. Now taking strains. So obviously strain in x direction is equal to 0, strain in y direction is also equal to 0, strain in z direction is also equal to 0 here. And these are all overall strains because they are combination of thermal plus mechanical cases because they are restricted. So restrictions will give rise to forces. So it's a mechanical case, and we are giving rise to temperature. So it is trying to expand freely. It's a thermal case as well. So now to get the value of sigma, which is not known to us, let's take this condition. Observe carefully, everyone. So we have the condition that epsilon x overall is equal to 0, which is actually the combination of epsilon x thermal plus epsilon x mechanical. And again, for mechanical strains we have these formulae, never forget them. So overall strain is equal to 0. Thermal strain is obviously alpha delta T. Mechanical strain is according to this formula. Okay, but here everything. Okay, so those values are sigma here. So this becomes alpha delta T plus sigma by E minus mu sigma by E minus mu sigma by E. So this becomes 0 is equal to alpha delta T plus sigma by E whole into 1 minus 2 mu. This gives us stress value is minus alpha delta T into Young's modulus whole by 1 minus 2 mu. So this is the answer for this question. I mean for this example. In fact, there is a gate question which is asked directly based upon this formula. Two questions. One question is compulsory or one question is directly the derivation. So solution for the question is directly the derivation. Another question is based upon this formula. So you can use the formula, you can get the answer. Okay. Anyways, kindly copy this. We'll go ahead with the next one. Another two cases are there and then we'll be completing this. So this derivation is very important. How we are taking this condition to get the unknown value sigma. It's very important. You are telling that we can remember this formula, right? Okay. We have other two cases. If you are able to remember all these formulas, that's fine. But if you understand this condition, you can do on the spot. You can derive the equation on the spot there. It becomes easy. Completely your choice there. I prefer to remember this thing here because this condition is very obvious from the equation, so we can apply. So everyone done? Shall we go ahead with the next one? Two directions constrained, another direction is free. So two directions are constrained, another is free. So what I'm taking is, it is constrained in x and y. And it's free to expand in z direction. So this gives you sigma x non-zero, sigma y non-zero, sigma z as 0, and epsilon x, epsilon y, epsilon z overall. So it is restricted in x direction, so and y direction, so strains are 0. This is non-zero. So we should get these two non-zero values and also this non-zero value. This non-zero value you can get from this condition, the way in which we did in the previous example. So you also can do simultaneously along with me. You can get the correct answer before me as well. Okay. So I'm doing it. Epsilon x overall. It's epsilon x thermal plus epsilon x mechanical. 0 is alpha delta T plus epsilon x mechanical means sigma by E minus mu sigma by E minus mu 0 by E. This gives us alpha delta T is equal to sigma by E into 1 minus mu. This implies sigma comes out to be minus alpha delta T into Young's modulus whole by 1 minus mu. So we have to get epsilon z overall also. So same condition we'll take it. Epsilon z overall is equal to epsilon z thermal plus epsilon z mechanical. So thermal is alpha delta T, mechanical is sigma z by E. So that is 0 by E minus mu sigma by E minus mu sigma by E. This comes out to be alpha delta T minus 2 mu sigma by E. So substitute sigma value from here. You can get alpha delta T minus 2 mu by E into minus alpha delta T into Young's modulus whole by 1 minus mu. So if you simplify this, you'll get the value as E and E will go, alpha will go 1 plus 2 mu by 1 minus mu. So you'll get 1 plus mu by 1 minus mu. This is the epsilon z overall. So what are the free expansion is happening? This is equal to this much here, corresponding to epsilon z overall strain. If you're done with this, we'll go ahead with the last one and then we'll see numericals. So two directions free and third direction is constrained. So it is simply nothing but the example which we took for linear changes. So in x direction it is constrained. So sigma x is equal to sigma. It is free in y direction and z direction. So sigma y, sigma z are 0. Now if you take epsilon x overall value, epsilon y overall value, epsilon z overall value, obviously these are this is 0 and these are non-zero. So you should get this non-zero value sigma and you should get these two values also here. So this thing we already calculated. Again we'll take this condition. Sigma is equal to minus alpha delta t into Young's modulus. So this is the formula which we already derived, okay, already known to us. So let's get these two values. So if you go by this, epsilon y overall thermal plus epsilon y mechanical, overall strain we don't know, we have to calculate this. Thermal strain is always alpha delta t. Mechanical is sigma y. Sigma y is 0. Sigma x, that is sigma. Sigma z, that is again 0. So alpha delta t minus mu by e into sigma. And we know the value of sigma as minus alpha delta t into Young's modulus. This gives us alpha delta t into 1 plus mu. So this is the value of epsilon y overall. If you do the calculation for epsilon z overall, you will get this as same value. So we get it as alpha delta t into 1 plus mu. So this is the answer for this question here, or this case here, okay. So by looking into this question, next slide, you can give me answer very easily. Yeah. So for this question, there is nothing extra to study because it's a very direct question. So they taken the second case where the body is restricted in all the three directions. So what is the value of stress? So the derivation has already given us the answer as A. So the answer for this question is A, minus alpha delta t into Young's modulus by 1 minus 2 mu. Okay. Let's go to the next question. It was asked in 2019 exam in mechanical engineering paper. So it's given that a solid cube of side 1 meter is kept at a room temperature of 32 degrees centigrade. The coefficient of linear expansion of the cube metal is 10 power of 5 per degree centigrade and bulk modulus is 200 gigapascal. So alpha is 10 power of minus 5 per degree centigrade. The given bulk modulus here 200 gigapascal. If the cube is constrained in all directions, all around, and heated uniformly to 40 degrees centigrade. So here we can say delta T is equal to 10 degrees centigrade. Temperature is rising here. Then the magnitude of volumetric mean stress induced due to the heating is. So we have the formula for this case as minus alpha delta T into Young's modulus by 1 minus 2 mu. But we don't know the value of E and Poisson's ratio mu, but bulk modulus K is given. So we can easily get the answer because we have the formula for relationship between bulk modulus, Young's modulus and Poisson's ratio like this. So we can write down this E by 1 minus 2 mu as nothing but thrice K. This implies volumetric stress, or the stress is nothing but alpha delta T into thrice K. So minus alpha, that is 10 power of minus 5, delta is 10, thrice K, 3 into 200 into 10 power of 9. So here we see that 9, 10, 11, 12, 10 power of 12 minus 5, 12 minus 5, 10 power of 7. So it is nothing but minus 60 megapascal. So 60 megapascal compressive. So 60 megapascal is right answer only. You guys can give me answer for this question. I think it's the last question. We are done with this chapter. So for this, it's given that a steel rod of 10 millimeter in diameter and 1 meter long is heated from 20 degrees centigrade to 120 degrees centigrade. So delta T is equal to 100 degrees centigrade. Young's modulus is equal to 200 gigapascal. Poisson's ratio is 0.3. And coefficient of thermal expansion is 12 into 10 power of minus 6 per degree centigrade. if the rod is not free to expand along the lengthwise direction, the strain developed in the lateral direction is. So we have derived lateral strain on epsilon y or epsilon z as alpha delta t into 1 plus mu. Is it right? I hope it's not there is no mistake in this. So if you substitute 12 in 10 power of minus 6 into delta t, that is 10 square 100, 1 plus mu 1.3. So this gives you 12 into 1.3. Okay. So So 156 into 10 power of minus, so here 6 minus 6 plus 2 minus 1. So minus 5 plus 2. Minus 7 plus 2 minus 5. So this becomes 0.00156. This is the answer for this question. Clear? So tell me, we are coming to the summary here. Brittle materials undergo plastic deformation, yes or no? We're looking at the summary of this question, of this chapter here, first chapter. The answer is no. Very good. Brittle materials cannot undergo plastic deformation. Only ductile materials can undergo plastic deformation. Ultimate stress is the stress the material can take up to failure. Is it true or false? It's true or false? The answer is false. Ultimate stress definition is the highest value of stress the material can take in a conventional stress strain graph. Okay, so if you are taking ductile material, failure stress or stress at failure will be yield stress, okay, which will not be equal to ultimate stress, because ultimate stress will be far higher than that. But in brittle materials, the stress at failure will be equal to ultimate stress. So this statement is valid only for brittle material, it is not valid for ductile material. So we can say the answer is false for this one, or no. Third one, Hooke's law is valid for only mechanical cases of stress and strain. True or false? Or yes or no? So Hooke's law is valid only for mechanical cases of stress and strain. We understood that. So the answer is true for this. Last one. In fact, it's a gate question as well. Poise ratio of incompressible material is how much? No, Ankit. I'm not talking about rigid material. I'm talking about incompressible material. For rigid material, we take it as 0. For incompressible material, it is equal to 0.5. Clear, Ankit? Don't get confused. Understood? This completes our first chapter. After this, we'll be going with the second chapter. So earlier, we used to go with analysis for stress and strain as a second chapter. Okay? But this time, I would like to go with shear force diagram and bending moment diagram, because shear force diagram, bending moment diagram is completely equilibrium condition. So there is nothing extra to learn. So, and also if you are completing shear force diagram, bending moment diagram initially as a second chapter, you will get time to do practice. So over the time, whenever you get some doubt, you can ask me in the classroom itself. Clear? Instead of solving it or explaining it now, if I solve it later, you will get less time to interact with me. Anyways, I would like to take the second chapter as shear force diagram, bending moment diagram. I suggest everyone not to miss this lecture, because whatever you would like to do in the third chapter and fourth chapter is completely depending upon this second chapter itself. Unless and until you don't know how to draw a shear force diagram, bending moment diagram, you don't know how to get shear stress in a beam and bending stress in a beam, and also you don't know how to get slope and deflection in a beam. Understood? So all these three chapters, whatever you're going to do after this, second chapter, third chapter, fifth chapter, second chapter, third chapter and fourth chapter, are completely related with respect to each one of it. So I advise you people not to miss that lecture. Understand, it becomes very difficult. Okay,